everyone's here. Good. Okay, so today we're going to talk about directivity of loudspeakers. There is some homework for this, but I'm not going to give it to you until Monday because I don't want you to start on it until after I've told you what I'm going to tell you on Monday. Because if you start on it over the weekend, you're going to imagine things that I don't want you to imagine. In other words, I want you to make choices that are actually motivated by actual information, not choices that are motivated by equipment that you think looks cool and things you've seen other people do, which is, I want you to actually decide something based on data, okay? But the assignment is basically going to be, I'm going to ask you to design a loudspeaker system for one of our spaces, okay? Just a simple one, but I want to make sure that you're going to do it the right way and not just do what you've seen somebody else do or put the speaker in there that you've always wanted to use for no other reason than you've always wanted to use it, okay? So, yes, informed choices. And by the way, that's like, you know, if you really want to like depress me just in the future, give me a whole stack of show paperwork for a show that you've just like done because I told you to do it. That clearly you decided before you did any of that paperwork what you wanted to do. Like you went into this saying, I know exactly what I want to do. It's this, and this. And now I'm going to create all the paperwork that Jason makes me create to show that. And that just kills me inside.
So like instead of doing something for the good of the show.
Well, no. So instead of using that process of all of the paperwork and things that you have to do, instead of using that to figure out what it is you should do, you decide what you're going to do first, and then go through this laborious process of creating all this paperwork to prove something that you decided with zero data. Okay. Like that just depresses me because I feel like, wow, you just wasted all of your time and my time, and now we have to look at this paperwork that clearly is meaningless because you already decided what you were going to do before you ever even touched any of this. Okay? So don't do that unless you really want to make me sad.
Got it.
Okay? So I'm going to give you some of the information today that will help you through that process, okay? So loudspeakers, you know, we sort of know what they do. They generate sound, right? Or rather, if we want to get particular, they are transducers that convert one form of energy into another form of energy. Specifically, they convert audio into sound, or electrical energy into acoustic energy, okay? That's what they do, okay? So you feed electricity into a loudspeaker, and it converts that into sound, or acoustic energy, all right? And then it disperses that acoustic energy everywhere, really. But it doesn't disperse it everywhere evenly. Naturally, with some exceptions, the loudspeaker, if left on its own, would, for the most part, distribute that energy everywhere equally. But we don't really want that usually, okay? Exceptions to that would be like these dodecahedron loudspeakers that we've made. Those are specifically designed to distribute energy equally in all directions. But usually we don't want that. Can you think why we would not want the energy to go equally everywhere? Yes, but why would you not want it to go some places but want it to go other places?
You can create destructive interactions.
Yes, that's a good one, right? We know that when two similar sounds run into each other in air, they can get in a fight. So we might not want that to happen, so that we would like to be able to direct the energy in a certain place and another. Good. What other reasons?
Focusing energy where there doesn't need to be, so you're literally just wasting energy.
Yeah.
Yeah, that's what I was
Right.
gonna say.
So if we're using all of this energy to all this gain and amplification that we're going to build into our system to spray energy out where there aren't any ears, then that's a waste, right? We could be putting that in a direction where there are people and ears, and that would be better, right?
Yeah.
Okay, so those are a couple of there's a lot of reasons, right, why we would want sound to go one place and not another place. Feedback is one of them, right? We certainly don't want the energy coming, usually we don't want the energy from our loudspeakers going into our microphones, because that can generate feedback if you do it wrong. So we would like to point the sound where the audience is, but not where the microphones are. Okay, so there are lots of reasons why you would want to direct the sound energy in one direction but not another. Okay, and there are various ways that we can do that and accomplish that. I will say this is not a class on designing loudspeakers. Okay, we're not going to get into that. Okay, but what we will get into is talking about things that you should be aware of about loudspeakers that other people have designed, and how you might expect them to behave based on the way they've been designed. Okay, so the first thing I want you to understand is this notion of directivity. The way that we can make a loudspeaker direct the energy in one direction or another is by confining it. Okay, so naturally the loudspeaker driver is going to want to spray the sound more or less everywhere, within some limitations of its physical geometry that we'll talk about in a moment. But generally, it's naturally going to want to go everywhere. And so one way that we can, the primary way that we can direct the energy in one direction and not the other, is by confining it in some way. In other words, we don't necessarily have to do anything to the loudspeaker, but if we can put obstacles between the loudspeaker and the place where we don't want the sound to go, then we can focus the energy in the direction we do want it to go. For example, if we just take a loudspeaker that's in the middle of the room and put it up against a wall, well, then all the energy that would normally be directed towards the wall, if the wall is a reflective surface, will reflect off that wall and go the other direction, right? So we can confine that energy so that it doesn't go behind the loudspeaker. So anyway, that is kind of the main tool we have at our disposal for directing the sound in one direction or another, is by confining it. And there are ways that we can measure the degree to which we are confining the sound. And we call that the directivity index and the directivity factor.
So the radiator is a speaker?
Yes.
Okay, that was confusing.
So, there are lots of things that could make sound, right? We're talking about loudspeakers primarily, but there are other things too. But yes, we're just calling this, in this case, it's a radiator. Radiating sound. So directivity index is the amount of sound SPL increase you get as a result of confining the dispersion. Okay, so if you take the energy that normally wants to go everywhere and confine it so it's only going in one particular direction, then the place where the energy is directed will be louder than it normally would be, right? Because all the energy that would normally be going to the back is now going to the front, and that's going to double up and you get a boost. Okay, so it's going to get louder as a result of confining it. That's the other reason why we would want to direct the sound in one. That plays into the efficiency point of view. Is we don't want to waste energy sending the sound in a direction we don't need it, because if we can avoid that, then we can make it louder in the direction that we do need it. Okay, so the directivity index is a value in dB representing the amount of increase we get as a result of confining the dispersion of the sound. The directivity factor is sort of a ratio between the SPL level in the direction the loudspeaker is going. It's a ratio between unconfined loudspeaker and confined loudspeaker, right? So we confine it, we get an SPL increase that we call a directivity index. The directivity factor is the difference between what we measure when it was confined versus not confined. Okay, and there are lots of ways we can confine it. I talked about one of them. Walls, right, is one of them. Boxes is another one, right? Most of the loudspeakers that we work with sit inside of boxes. Okay, and the box is a way of confining it. Okay, so there's all this sound that's going to be coming off the back of these drivers, but it's in a box, right? And so it's called an infinite baffle. So a box that wraps around is the same thing as building the loudspeaker into a wall that goes on forever. Okay, So you are confining the sound by putting it inside of something, okay? And one of the advantages of that is it gets louder, okay, in the direction that the sound is allowed to disperse, okay? Now, some of you, like, some of the things that like Brett is experimenting with is saying, well, there are other ways to confine the sound, but you have to sort of liberate yourself from the box in order to do that. And in order to do that, you lose other things, right? Like your directivity index bottoms out once you remove the box, okay? But you can get other advantages. So there's, everything's a trade-off. But a box is one way you do that. You can stick a horn on it. You've seen you've seen horns that get stick inside of loudspeakers, and then there's a little driver on the back of that horn. Well, the horn is designed to confine the dispersion of the sound within a certain area, okay? Walls, baffles, all kinds of things, right? These are all ways that we confine the sound and keep it from going where we don't want it to go, all right? So let's take a look at this relationship between directivity index and directivity factor. So I have over here on the left this thing that looks like a little sunburst. That's, that is some sort of sound radiator, something that makes a sound, okay? We could call it a loudspeaker if you want. We could call it a person talking. We could, whatever. It's the thing that makes a sound, okay? And then at some distance away, some length away, we can measure the sound pressure level with a SPL meter, okay? So that's what's over here on the right, is an SPL meter. We're just measuring how loud the sound is coming off of that thing, okay? In this case, our directivity index is 0 dB because we're not confining the sound in any way. Therefore, we get no increase in level as a result of that confinement, okay? So totally unconfined sound generating device or radiator, we get directivity index of 0. The directivity factor is 1, or a Q of 1. So Q is another term used for directivity factor. Q, you run into the concept of Q in two places. One is in filters, like EQ filters. There's on parametric filters, there's usually a Q adjustment.
What does the Q stand for?
I don't.
We were just talking about this, and we were like, we know it does, we don't know what it is.
I don't actually know. I could pretend to know and make something up that might be right, but I'd rather not.
The Q represents the directivity factor?
Yes.
Okay.
And the best way I've think about Q is it's about a factor of confinement. Okay, so whether you apply it to an EQ filter, it's the extent to which you're confining the range of that filter. In this case, it has to do with how much you've confined the dispersion of the sound. Okay. In this case, we have a Q of 1, or a directivity factor of 1, because it's a 1-to-1 ratio between confined and unconfined sound. Did you just look it up?
Stands
Okay.
for quality.
Quality, interesting.
The quality of the piece.
I'm not sure about that.
Not science.
That sounds made up. That's. I was going to say something like quotient or something, but I don't know that that's right.
So Q is how much you've confined the sound?
It's a ratio between the intensity of the confined sound versus the unconfined sound. Okay. So the more you confine it, the louder it gets in the direction that you've confined it. And the Q is the ratio, or the difference between those two levels, confined or unconfined. So in this case, it's a ratio of 1-to-1, a Q of 1, because we have 1-to-1 difference between confined and unconfined, because we're not confining it, and therefore there is no difference. Okay? Now let's try to confine this sound a little bit. So if we put it up against a wall, and just pretend this wall goes on forever, what happens is, effectively, all this energy that used to go that direction is now not going to go that direction anymore because there's a wall there, right? And the wall will not allow the sound to go that. So where's it going to go? That energy, it doesn't disappear, has to go somewhere. And if the wall is not going to allow that sound to go through, then that energy will reflect off the wall and go the other direction. Okay? So we've now, in the direction where we're measuring, we've now doubled the energy. Right? Because half of the energy that was being radiated from that device is not going the direction it used to go. It's now folding back onto the other half. So, and we know that when you get into the air and you double sounds in the air, you effectively get a 3 dB increase. You could get a full 6 dB if the phase was perfectly aligned. So like for subwoofers, when you do this, you usually get 6 dB when you put it up against a wall. Because the wavelengths for sub-bass are so huge that even that extra couple of feet from bouncing off the wall and coming back is not enough to get you past that 120-degree phase shift to cause any sort of cancellation. So for subwoofers, you usually get 6 dB per wall, which is really cool. Well, I'll get into that later. But there's a cool rule of thumb that you can keep in mind about subwoofers for that. So in this case, our directivity index is plus 3 dB because we have a 3 dB difference between when the sound was confined and when the sound was unconfined. Right? It got 3 dB louder in the area where we're measuring because we folded half that energy onto the other half. And in this case, our directivity factor is 2, or a Q of 2, because it's a 2-to-1 ratio between the intensity of the confined sound and the unconfined sound, because we doubled it, right?
So this is assuming that your radiator is radiating in 360 degrees.
Yes.
But what about, so the speaker, assuming it's a loudspeaker, is aimed at the wall. You've got your higher frequencies, which are not omnidirectional coming out of it. Do you still get any kind of boost from the reflection off the wall? Or is this really more of just a lower frequency?
So this is, well, no, this is true assuming that the sound that you're measuring is naturally wanting to go in all directions. Okay? If it's not naturally wanting to go in all directions, then yeah, you would not necessarily get that boost.
Okay.
But you're about 8 slides ahead of me right now. So if you'll if you'll hold that thought for a minute,
Yeah.
Long
then
story short, yes, it is. Speaker theoretically just the lower frequencies. Then, if what you just said is just the lower.
well, no, I mean, not necessarily.
It depends.
Oh boy.
Depends on a lot of things.
Also, in physics and engineering, the quality factor, Q factor, is a dimensionless parameter that describes how underdamped an oscillator or resonator is. So it's the. So it actually.
All right. Well, whatever. Yes.
Can you just one more time explain what the directivity index, what that number represents?
That 3 dB.
It's a boost that you get?
Yeah. So remember, this little thing here is an SPL meter.
Right.
And we're measuring how loud the sound is. And when we measured how loud the sound was when there wasn't a wall, we got some certain level, whatever it was. Okay?
It was 0.
Yeah.
Or 1, I think.
Well,
No, it
0.
was 0. Yeah,
right?
It was 0.
Because there is no directivity at this point, right? We've not confined it in any way. So what we measure is that is our reference point.
Okay.
Our reference level in this case is how much sound do we get when we don't confine it.
Okay.
Okay? So then we confine it by putting it up against a wall, and we measure it that same distance away now, and it's going to be louder because some of that energy is now coming towards us that used to be not coming towards us. So it's now louder, 3 dB louder, in fact. And so the directivity index is plus 3 dB because we had a 3 dB increase as a result of confining the dispersion of the sound. Okay. Let's try to confine it a little bit more, shall we? So what if we put it against the wall and the floor? So in that corner, now we've confined it twice. Okay? So in this case, it's still half the energy that used to go backwards is coming forward, but now half the energy again that used to go down is going up. Okay? So we're now confining it twice. We'll get a 6 dB increase in that case if we measure at the same distance now. We had to change our measurement angle a little bit because the dispersion is now heading in a slightly different direction, but the distance is the same, and we would at that same distance moving the measurement at the angle where the energy is focused, we get a 6 dB increase now because we have folded the sound onto itself twice because there's two walls. And now our directivity factor is 4, or a Q of 4, because it's a 4-to-1 ratio between the level we measured when the sound was unconfined and the level we measure when we've now confined it with two walls, okay? Because we doubled it twice. So it's a 4-to-1 ratio and a 6 dB increase. So a directivity index of +6, directivity factor of 4, or Q of 4. We could confine it some more still, right? What if we could add another wall and we could put it in that corner with the other wall? And now we've confined it 3 times, folded it over itself 3 times. Again, we have to change the measurement angle slightly now because now the energy is going to be focused in a slightly different direction. But as long as we keep the distance the same, we would then at that point measure an SPL increase of 9 dB. Okay, so you're getting 3 dB per wall in this case. 6 dB per wall for subwoofers. And now our directivity factor is 8, or a Q of 8, because it's an 8-to-1 ratio between the confined sound and the unconfined sound, because we've doubled it 3 times now. Yeah? Each time we add a wall, we've doubled the sound onto itself again. Every time we do that, we get a 3 dB increase, and our Q doubles as well. Okay? So we haven't had to spend any money so far, and we've gained ourselves an extra 9 dB just by confining where the sound goes. This is a big reason why we put loudspeakers inside of boxes, is because they get louder when you put them inside of boxes. Okay? Now, and as I say, with subwoofers, this would be an 18 dB increase, right? Because you get 6 dB per wall with subwoofers. That's 18 dB that you get for free. That doesn't require bigger amps, doesn't require more sensitive loudspeakers. The subwoofers tend to be omnidirectional anyway. So if you can just put them in a corner, you get an extra 18 dB for free. Okay? All right? So that's just something to keep in mind. Like, there's no reason not to do that, right? Because it's free. Free sound.
I have a question.
Very rarely do you get free sound. This is one situation where you do.
Does the sound actually get louder, or does it just go in one direction a lot more, so it's like perceived as being louder?
So there is a certain amount of energy involved in this radiator, right? And all we're really doing is, if we don't confine that at all, any single place where we measure it will only be a small portion of that total energy that's available, because the rest of it's going other directions.
Right.
So if we can take that energy and direct it better, then yeah, it gets louder.
Yeah.
It gets, because there's more energy focused in the direction that we care about.
Okay.
So this is just kind of a very, very simple example of how we can start confining the sound and why we would do things like put loudspeakers in boxes or mount them in walls. Things like the things that you've seen people do is because it gets them louder and it helps focus the energy in the direction that we want it to go. Now, how do we document this? Right? How do we? If you're going to pick a loudspeaker and figure out if it's going to go where you want it to go and disperse the sound the way you want it to disperse, there has to be some way that you can see and measure and understand how it disperses the sound. So there are lots of ways that we do that. Oh, sorry, I forgot about this slide. So there's a mathematical relationship between directivity index and Q. Okay? And this math should look very familiar to you by now. So a directivity index is equal to 10 times the log of the Q. And the Q is equal to 10 to the power of the directivity index divided by 10. Okay? I'm not going to make you do that math. There's not, even for the assignment, it's not, it's not particularly important. But for our purposes. It's not. It's important if you design loudspeakers and horns and stuff like that, but we don't. So, but I just want you to see that that's the relationship between these two values. Okay, they're connected to each other. Okay. So how do we document this? Well, here's one example. One example is called a polar plot. So these are all ways that somebody's going to design a loudspeaker and they're going to try to sell it to you, and they're going to try to explain to you what it can do directivity-wise. You know, how does it disperse the sound? One way they might show you this is using a thing called a polar plot. So a polar plot is going to show you the dispersion of the sound for a single axis and a single frequency. Okay? So if you want to get a sense of what it's going to do for all the frequencies and for all the different axes, all the different ways you could slice that loudspeaker and look at it, you're going to need hundreds of pages of polar plots. Okay? So this is not a particularly efficient way of documenting loudspeaker directivity, but it is relatively simple to understand. Okay? So let me sort of see if I can explain how this works. So when I say one axis, what I mean is this would be, let's pretend that, here's the loudspeaker, and we're looking down at it from above. Okay? And so what this is showing us is how it disperses horizontally. Okay? But it might also show how it disperses vertically. Right? It could be that we're looking at this from the side of the loudspeaker. Right? So this would be the top over here, and this would be below it over here. Okay? But let's just assume for now that it's horizontal. So, over here, that would be, if we're looking at the loudspeaker, this would be the left, right? And this would be to the right of the loudspeaker if we're looking at it from the front. In this case, we're looking down at it from above, and we can sort of see what it does. So what happens is this solid line here, the solid black line, represents the level or amplitude or sound pressure, whatever you want to call it, for a given frequency. So let's just say it's 1,000 hertz. So 1,000 hertz, this is what will happen. Up here is 0 degrees, so that's considered our reference point, is the on-axis response, because usually the loudspeaker is the loudest at that 0 point, right? When you're staring straight at it on both the horizontal and vertical axis, is pointed right at you. That's when it will be the loudest for every frequency, usually. So now, as we move over to the right or left, so if we go 30 degrees over to the right here, it's dropped down. This grid, this polar grid, has these little thin circular lines. And each one of these represents a certain difference in level. And usually the polar plot will tell you it's usually 6 dB per thing, per line. It could be 3 dB per line, could be 5 dB per line. Just depends on how they want to plot it. Usually they want to plot it in the way that makes it look the best for the marketing people. So it's important that you figure out, well, what is this? 3 dB per division, 6 dB per division? Well, let's assume that it's 6 dB per division. So that means, by the time we get to 30 degrees, we're not even halfway between these two. So we haven't even gone 3 dB yet. But when we get to 60 degrees off axis, it is now 6 dB quieter at 1 kilohertz.
So meaning that if your ear is at that point.
Yep. If this is you will hear 1 kilohertz 6 dB quieter than the person over here.
Got it. Okay.
Right?
It wouldn't be 3 dB up there.
It would probably, it'd be almost 3 dB here, right? So this person is 3 dB, minus 3 dB over here.
So when you see a dispersion angle for a loudspeaker, is it usually where the 6 dB drop is, right?
Like in a spec sheet or something when they say, so this is,
It changes per frequency.
yeah, so that 6 dB point, that's sort of that's the point of no return for most situations.
So at 1K, that would be 120 degrees.
Yes. So what will happen is if you buy a loudspeaker, they'll say, in this case, assuming they used 1 kilohertz as
Yes.
the frequency that they were going to spec, then they would say this loudspeaker is a 120-degree horizontal dispersion loudspeaker, right? Because you go 60 degrees to either side to lose 6 dB, right? And once you've got more than 6 dB, then that's considered too much loss, right? At that point, it's got too quiet for you to really be okay with that, okay? So if you went 90 degrees off axis with this loudspeaker, how much quieter are we now?
12 dB.
Yeah, so we're minus 12 dB now over there. And then to get our other 6 dB to get to 18, we'd have to go to 150 degrees off axis. You see that? So this would be, that would be our minus 18, right? This is assuming 6 dB per division, which I think it probably is. Does that sort of make sense?
Yeah.
You get how that works? So here's the catch. This is only for 1 kilohertz.
Yeah, that
Okay.
would be my next.
So we would, if we wanted to get a sense of what this would do across the entire frequency spectrum, we would need to look at a different polar plot for every frequency. Usually they would do this in octave bands, so at the bare minimum octave bands, right? So they would say, here's 1K, here's 500 hertz, here's 2 kilohertz, 4 kilohertz, 8 kilohertz, 16 kilohertz, you know, and then they go down 500 hertz, 250, 100, so on and so forth, okay, 50 hertz. And then you'd also have to then do it for the vertical, because this is only for the horizontal axis, right? So then we'd have to have a whole other set of octave bands for the vertical side as well, before you could really get a sense of what this thing can do. Because ideally, you would like all the frequencies to be confined in the same way, right? It's not like this person sitting at 60 degrees is going to be okay with hearing 1 kilohertz 6 dB quieter, but 4 kilohertz 12 dB quieter, right? They're going to want to hear all of the frequencies more or less the same level, okay? And this is now where it gets really complicated from the point of view of someone who's trying to design this loudspeaker, is how do I pull that off? Because it's not naturally going to want to do that for reasons that we'll see a little bit later. So this is one way of documenting the directivity of the loudspeakers, using a polar plot. It's not a very efficient way, but it's relatively simple to understand, and you know, it works. But as I say, not particularly efficient, but probably the most common way of documenting this. Okay, let's look at another way. So this is called a beamwidth plot. So given this idea that the 6 dB down point, as we call it, is sort of, that's the range that you really want to consider. Once you've lost more than 6 dB in any direction, then at that point the loudspeaker stops being very useful to you. Okay, so this is a plot that shows you the 6 dB down points for each frequency. Okay, so and this would be, they call this the beam width. So if it's 30 degrees on either side is where you drop 6 dB, then that would be a total of 60 degrees dispersion angle, right? That would be a 60-degree bandwidth or beam width. So this is showing us for both the horizontal and the vertical axis. And you can sort of see this. Now, this is very common. This is not an unusual beam width plot. The low frequencies are basically omnidirectional. Okay? So their beam width is 360 degrees at about, 120 hertz and below. So those frequencies are going to go everywhere. Yes?
Is this just to make it easier, or why are the lines spaced out the way they are on charts like this?
What do you mean?
Like they're not spaced out like a normal graph would be spaced out where they're all even.
Oh, well, so very good question. So this is called a logarithmic plot as opposed to a linear plot. If it was linear, then basically all of these high frequencies would be crammed over here,
Okay.
right? Oops. So the reason for that, it has to do with the resolution of our hearing. Okay, so we.
I don't think it went back.
Yeah,
I
it
don't
did.
think-
It did.
Oh, it did. Okay.
So basically, we can hear differences in level across frequency spectrum in very narrow bands in the low end of the spectrum, right? So we can make very small ranges of changes down here in the low spectrum and still be able to hear it. But up here in the high spectrum, we would need to make a huge change. So whereas what I mean by that is here we could probably take a third octave worth of frequencies here, which would be, or even just like a range of 75 hertz, right? A block of like 75 hertz difference, right? And pull that down, and we would be able to hear that. But that same tiny range up here in the high frequencies would be too small for us to even hear the difference, okay? We would need to take in much more than just, plus or minus 50 hertz in order to hear that difference at the high frequencies. We have to make much bigger changes at the high frequencies. So that's why we plot them this way. Is called a logarithmic scale, in order to demonstrate the frequencies in a range that corresponds to the sensitivity of our hearing.
Gotcha.
Okay. If we did it linear, then it would be a graph all about the low frequencies.
Useless.
Yes, would not be particularly useful to us. So in this case, you can kind of see that our beam width more or less evens out here 2K and above. Right? So it's dispersing pretty consistently 2K and above. It's not perfect, but like look at this horizontal dispersion line. That's pretty flat, actually, in most cases. The vertical dispersion line would be what we mean by this is here at this frequency, we're 90, 80, 70. We're about a 70-degree horizontal dispersion before we get 6 dB down on either side. On the vertical, we're 20, 30, about 45 degrees vertical before we've dropped 6 dB on either side. So this is probably a 70 by 40 loudspeaker, which is pretty common. That's a common loudspeaker spec. 40 on the vertical, 70, 75 on the horizontal. Okay? And it stays more or less within that range for every frequency above 2K. Okay? It fluctuates here and there, but that's what real life is like. Okay? But below 2 kilohertz, it gets wider and wider and wider and wider and wider. Okay? So its ability to control the dispersion of the sound is greatly reduced as you go lower in frequency. It gets more and more omnidirectional as we go. Okay? So the advantage of plotting it this way is you can kind of see that 6 dB down point range for all frequencies, right? You can kind of get a sense of, assuming I can fit all of my audience area within this range, then I should be, this would be my frequency response, right? So if they were sitting at the 6 dB down point, right, or at, then in some cases there would be some frequencies would be quieter than others, right? So as you get off axis, the high frequencies get quieter faster than the low frequencies do, right? So as I keep moving to the left, things are going to get quieter. But it's going to be the high frequencies that are getting quieter in this case. The low frequencies, the really low frequencies, are going to stay the same, right? Because the low frequency, this loudspeaker is omnidirectional. So that's important to know. Yeah?
When it comes to that, the whole low frequencies traveling way farther than high frequencies, why is
Way farther? What?
This is sort of going off of this. I don't know if this is digressing too much from the current topic. I was just wondering how low frequencies go further than high frequencies. Like whenever you're outdoors, like train whistles, you'll hear mainly the low end of the train whistle than actually the higher stuff.
So that has more to do with absorption than anything else. Okay? So it's easier to absorb high frequencies than it is to absorb low frequencies, because to absorb the low frequencies, you need big things, right? So it's not, I wouldn't say that low frequencies travel farther than high frequencies. I would just say that,
in environments.
I would just say that high frequencies absorb more easily as they go further, right? It's just,
But that's it. That's
Yeah.
the only thing that affects that actually. So like if you were in theory like in a desert or something, then everything would travel.
yeah, without any temperature gradient and or wind gradient, and you know, free field, perfectly free field environment with perfect humidity, perfect temperature, even temperature, and you know, nothing in the way. Like you've got a really, really hard reflective ground.
The other stuff.
Like the ground is not porous and absorptive. You know, you're like at the salt flats or something like that where they do all the drag racing. You know, then yeah, that phenomenon would be greatly diminished. Okay. Yes.
I have a question about this.
Yes.
So this is representing, I guess the 6 dB down point
Mm-hmm.
is confusing me. Is this representing all the points where you are going to get a 6 dB
Yes.
decrease?
Okay. So what we're saying is, there's the loudspeaker, right? Now at some angle, you're going to get minus 6 dB. Okay? And you'd get, presumably, that same angle on the other side would also be minus 6 dB. Okay? That's called, this area is called the beam width. Okay? And so that angle, okay, so whatever degrees that is going to be different per frequency. For some frequencies, this will be a really wide beam width, and for some frequencies, this will be a very narrow beam width. And that's what this is showing us, is how wide is this for each frequency. So, for example, on the horizontal at 800 hertz, that angle is 100 degrees at 800 hertz.
And that angle, there's a 6 dB decrease? Or at
Yeah,
that-
so when it says 100 degrees, that means 50 degrees on either side. You will drop 6 dB for that frequency,
Okay.
right? However, over here, that's 90, 80, 70, 60, 50. So 50 degrees at, what is that, 16K? Okay, so you hit that 6 dB down point sooner at 16 kilohertz than you do at 800 hertz.
And that means that 25 and 25
Mm-hmm.
is where the decrease
Yeah.
is? Okay.
So essentially, if I diagram this a little bit differently, we could say that here's your loudspeaker, and so that would be your beam width minus 6 for 16
Yeah.
kilohertz. But this would be your beam width for 800 hertz.
Okay. And it's minus 6.
Minus 6, minus
Yeah.
6.
For
right?
some reason, the polar plot makes more sense to me visually than the beam
Well,
plot.
it depends on what information you're looking for. Okay, so what the polar plot tells you is what happens even after that 6 dB point. Right? So the beam width plot only tells you this single spot when it drops 6 dB, but it doesn't tell you how much it drops before you get to that angle, and it doesn't tell you how much you drop after you get to that angle. It's just this is assuming that all you care about is where's the 6 dB down point. You don't really
That's
care.
like the number.
And that's sort of because that's usually when you should start carrying, is at 6 dB down. So the advantages of the beam width plot is it allows you to look at all the frequencies all at the same time, whereas the polar plot doesn't allow you that. The polar plot only lets you look at one frequency and one axis at a time. Right? So it's just a trade-off. It's like, what do you want? Do you want to get a sense? Do you want to be able to look at one thing and see the entire frequency spectrum, or do you want to look at one thing and see all of the angles? Right? It just depends. And it's not that one is better or worse or easier to read or not easier. It's just it's showing you different information. Okay. here's another one. This is called a directivity plot, and you might see this if for like a horn. If you were going to, let's say you're designing your loudspeaker and you're going to put a horn on a driver, they would usually show you a directivity plot for the horn. And what this shows you is over here on the left, right? This is a scale of directivity index. So this is dB. And over here is directivity factor, which is our Q. So 1 to 1,000 and 0 to 30. Okay, dB and Q. And what this means is this is how much louder that this frequency will get when you put it through this horn. So before you have this horn, you'll have whatever your frequency response is for the loudspeaker, right? If you stick this horn on it, this is how much louder each frequency will get. So the horn not only confines the sound, right, and will focus it in one direction, but it will change the frequency response of the loudspeaker. Because some frequencies are going to get louder as a result of that confinement than others will. So for example, here there's your 16K again. 16 kilohertz is going to be the loudest now. And 100 hertz and below will be the quietest. And this is how you compensate for the thing that Kai's talking about, which is that there is this phenomenon that generally the further you go, the high frequencies will tend to attenuate faster than low frequencies for lots of reasons, because of absorption and temperature and humidity and wind and all these sort of things. It's harder to shoot the high frequencies further. So you put a horn on it like that does this, and you can compensate for that because you're going to start with the loudspeaker with those high frequencies boosted. And so by the time you get really far away, it's flattened out, right? So this is just another way of looking at it. Again, it's not right or wrong. It just shows you this information about directivity on a slightly different slice. Okay. This is another one. This is called Isobars. This is, in particular, this is one that D&B Audio Technic uses for all of their. So if you download the PDF data for any of their loudspeakers, you usually get one of these Isobars. It's very similar to the Beamwidth plot, but what they're trying to do is be able to show you more than just the 6 dB down point. They can show you as many as they want by just shading it differently. In this case, they're showing you 6 dB and 12 dB. So what they're saying here is, here's 0 degrees, and then for each frequency, so let's look at 1 kilohertz, for example. So at 1 kilohertz, you run into the 6 dB range. So anything that's in the gray area, that's considered 6 dB down. That's your 6 dB down range. You hit that 6 dB down point at about 35 degrees at 1 kilohertz. And same thing over here, about 35 degrees on this. So this would be a 70-degree dispersion at 1K on whatever axis this is, horizontal or vertical. And then you look over here at 4K, and you hit your 6 dB down at 20 degrees on either side. So this would be 40 degrees dispersion at 4K on this axis. But what's interesting about this is you can also then see at what point you hit 12 dB down, which would be when you get to the dark area here. That's 12 dB down. So this helps give you a bit more information in that Beamwidth plot format. The reason that D&B likes this is they're all about trying to keep this dispersion as uniform as possible across the frequency spectrum. So the perfect isobar for them would be one that did this, right? Because they want all the frequencies to be controlled the same way. It's not possible. But what they're trying to show you here is, hey, look how relatively flat that is. And really, it stays pretty relatively flat all the way through here. So that's pretty well controlled. And then look, we even pick it back up down here at 500 hertz. They're suddenly confining 500 hertz even more aggressively, and that's because of a cool little trick they're doing with using dual drivers that interact in a constructive way and a destructive way to pull this off. So that's what they're trying to show off here is, hey, look, we can control this thing all the way down to 500 hertz before it starts dropping out. Like most loudspeakers would start dropping out here. And they're saying, well, no, we can control it down to a lower frequency. That's a pretty cool trick. Okay. So this particular plot shows off the feature of this loudspeaker that they're the most proud of. They're the most proud of the fact that you can look at 500 hertz and see that 500 hertz is relatively tightly controlled. It's sitting there in like about a 50-degree dispersion angle. That's pretty cool. It's hard to do that at 500 hertz because 500 hertz is a 2-foot wavelength. So normally you would need something bigger than 2 feet in order to control that. And this loudspeaker is not bigger than 2 feet. So they're doing a pretty cool trick. OK, this is another example. This is called the family of off-axis frequency response curves. The idea being that, yes, as you go off-axis, the loudspeaker gets quieter, right? But it doesn't get quieter in the same way for every frequency, right? The high frequencies get quieter faster than the low frequencies do. So a different way of thinking about it is the frequency response. It's not so much that the loudspeaker gets quieter, it's that the frequency response changes the further off-axis you go. And so what you're trying to figure out is, well, how far off-axis am I willing to go, and how much change in frequency response am I willing to tolerate before, it's so bad that I wouldn't want anybody hearing that, okay? And so what this is showing you is the frequency response of the loudspeaker, how loud each frequency is for various angles. So the solid line is your on-axis frequency response for the loudspeaker. You go 10 degrees off-axis, and you get this sort of like small dashed line. So it's changing just slightly. You go 20 degrees off-axis. It's getting, these high frequencies are getting quieter, but the low ones are staying more or less the same. You go 30 degrees, and really kind of you get down to almost 500 hertz, and 500 hertz is getting quieter. Okay. What you want to see is whatever that point is where you hit 6 dB down, and it's hard to see in this angle, but you could look at the other plots for this particular loudspeaker and find out, well, what angle is the 6 dB down point? And it would show you the frequency response of the 6 dB down point. So let's say it's this 40 degrees, and you would say, well, okay, the higher frequencies have got quieter, but they've got quieter all the same way, right? So at 2K and above, all the frequencies got quieter by the same amount. And that's good, because that person sitting 20 degrees off axis is going to hear more or less the same frequency response, right? The low frequencies will be a little bit louder, but the high frequencies are going to decay a little bit, but they will decay at the same rate. So the show isn't going to sound different to that person, other than maybe just a little bit quieter. But from a tonality point of view, it should sound more or less the same, because the high frequencies have all decayed the same way. Now, if this line instead did that, then I would not be too happy about that, right? I would say, well, now that person sitting over at 20 degrees is not hearing the same sort of sounding show. So yes, it's quieter, but it also sounds different in its tonality. So this is just another way of looking at it. And that, by the way, is the way I usually prefer to think about it when I'm trying to figure this out, is I really try to think about the frequency response. So at what point does the frequency response degrade so much that I feel like I need to do something about that, right? And there are various ways that you would do something about it, but I just want to know when that happens. How far away can I get from this thing before the frequency response is such that I want to fix it? And I would fix it by adding another loudspeaker to pick up where that one leaves off, or various things. Okay. All right. So now we're going to get into what Jason was asking me a little bit earlier, which is that yes, so the reason that not every frequency disperses at the same angle is because the loudspeaker's ability to control the sound is directly proportional to the physical size of the loudspeaker. Okay, so here I have 6 polar plots here, and see if I can explain what's going on here. So this is, each polar plot represents the same loudspeaker. okay, at a certain diameter. Okay, so maybe 6-inch diameter, 1-inch diameter, doesn't matter. It's a certain diameter. And what we're saying here is how will it disperse various frequencies? So in this case, for this particular frequency, this is a frequency where the diameter of the loudspeaker is only 1/4 of the wavelength of that particular frequency. Okay? So the wavelength of the frequency that's coming out of the loudspeaker in this case, that wavelength is 4 times bigger than the loudspeaker. Okay? And if the loudspeaker is 1/4 the diameter of the wavelength of that sound, it can't exercise any meaningful control over that sound.
Would that be a 1/4 or less?
Yeah.
So anything under as well?
Yeah.
Great.
So basically any frequency that is 4 times bigger or more than the size of the loudspeaker will be omnidirectional coming out of the loudspeaker, because the loudspeaker is just not big enough to control it.
And when you say that it's, I know what omnidirectional means, but like, it's just gonna go where it's gonna go.
It means you can go any angle you want and it doesn't get quieter.
Oh, so that's good.
Well,
Or not.
maybe.
Maybe.
It's not good or bad, it just is.
Okay.
Right? Do you want 100 hertz to be shooting onto the stage?
Okay.
No.
Maybe, maybe. I mean, maybe.
Well,
Like
you're
if,
using wireless, why not?
well, if this is a dance concert, for example, and you want the dancers to hear the sub bass, maybe I would want 100 hertz to spray out on the stage, right? But if I've got a microphone right there and I'm trying to pick up something in the microphone that's 100 hertz as well, then maybe I would not want the loudspeaker spraying 100 hertz onto the stage. Okay, so now here we're going up to a higher frequency. Now this is now a frequency whose wavelength is twice as big as the driver, or the driver is half as big as the wavelength of this frequency. Still relatively omnidirectional. Okay, you can see that it's these lines are 5 dB per division. So it's starting to get a little bit quieter over here at 90 degrees off axis, right? Maybe we've dropped 3 dB or so. When the wavelength is twice as big as the driver can just barely begin to start controlling it. Okay, the sweet spot here is this one, where the diameter of the driver is the same as the wavelength of the frequency. Okay, so that frequency is the same size as the driver, and when that happens, suddenly this loudspeaker is able to really control that. Okay, now this is, those of you that are following along with what Brett's doing, if we look at the other half of this, it would do something like that. Okay, so this is that sort of dipole effect that Brett's trying to do. It starts controlling it, and then over here on the sides it gets really, really less, but then it'll balloon back out again on the other side, right? So that's kind of interesting. Normally we don't pay a whole lot of attention to what comes out of the back of the loudspeaker, but if you did, that's what you would see. So that's really interesting. Okay, once you can put a frequency through that loudspeaker where that frequency has a wavelength the same size as the loudspeaker, that loudspeaker can start controlling that frequency. It'll control where it goes. It won't let it go over to the side. It'll focus that energy in front. And in this case, we're at a directivity index of plus 10 dB in that situation. So that loudspeaker will disperse that frequency 10 dB louder than lower frequencies that it can't exercise control over. That's pretty cool, right? However, it gets not so good once you get higher. So now we get to a situation here where now the loudspeaker is twice as large as the wavelength of this frequency, and it starts beaming it, actually. So now it's very, very tightly dispersed. And in fact, it starts doing these little ripples down on the side. These are called the little lobes, okay? You keep going up. Now in this case, the loudspeaker is 4 times as big as the wavelength of the frequency. Gets even tighter, right? Now it's 6 times as big as the wavelength, even tighter, and you get more little lobes here, okay?
Does it able to control more or what?
More, yeah. So essentially, while this frequency that is significantly larger than the loudspeaker will be omnidirectional. It'll go everywhere. This frequency will only go, in this case, it looks like in a little 5 or 10 degree axis before you drop 6 dB, or really a lot of dB, right? So now this loudspeaker becomes a laser, right, at that frequency. Yeah?
What causes the lobes, and is that similar to what a shotgun mic has with its polar pattern? Because I've seen that shotgun mics have something that looks similar to that, or is that just because they're both using
Similar idea. So it has to. I don't want to get too much into the detail there because I don't even fully understand all of it. But if you think about it, so the loudspeaker is really large relative to the size of so the wavelength we're talking is like a wavelength this big, okay, coming out of this loudspeaker, okay. Well, the whole loudspeaker is going to be moving, right? It moves as one whole thing to try to create that. And you see how it's angled, right, as it comes out a little bit. So all of it's trying to do the frequency, and because it's physically so much smaller than this, it creates destructive phase interactions, okay, because that frequency is coming out of this loudspeaker at different times as you get further away from the center, okay? So you get these destructive, and it's like comb filtering basically. Okay, and so as you go along there, it creates these ripples. So as you travel away from the center of the driver, there are times where it's reinforcing and times where it's canceling out, just because of the physical geometry.
It's so damn small.
Yeah.
Okay, and does that, and if so, how does that relate to shotgun mic patterns?
So shotgun mics, the way they work is it's a similar concept but different. So a shotgun mic is sort of really long like this. And it's going to have kind of a vented opening here for the sound coming, but then it's going to create other vents along the side here. And what happens is, so a sound that hits it from this direction is going to come in really strong here, but sound that comes at it from this direction is going to come really strong into the sides, but some of it will wrap around here, and you'll get destructive interactions inside of there because it's going to come into the top at a different time than it comes into the side, and therefore it'll cancel out. Okay? Whereas things that come directly in front of it don't have that same effect, right? It's not going to have an extra copy of itself over in the side to get in a fight with.
But some of the stuff still gets through, which is where those little lobes come from.
Yep.
The polar patterns.
Yep.
Okay.
Exactly. Okay, so the take-home message about this particular slide here is that, generally speaking, loudspeakers, their ability to disperse the sound gets narrower and narrower and narrower as you go up the frequency or spectrum. Okay, that's the first thing you need to understand. Generally, loudspeakers are omnidirectional for low frequencies and very narrow for high frequencies. Their ability to control the sound is directly proportional to how big they are. Okay? So the bigger the loudspeaker, the more it's going to be able to control lower frequencies. So if you want to control, let's say you want to control the dispersion of 100 hertz, right? You want 100 hertz to do this, right? Be relatively narrowly confined. How big would the loudspeaker have to be?
1 foot diameter.
A lot bigger than 1 foot.
10 feet.
10 feet, right? So what's the wavelength of 100 hertz? Remember how to do that?
1,000 divided by lambda.
Yeah, 1,000 divided by 100 hertz. So speed of sound divided by the frequency. 1,000 feet per second divided by 100 is 10 feet. So the wavelength of 100 hertz is 10 feet, which means the loudspeaker would have to be 10 feet in diameter in order to control 100 hertz. So why is that important to know? Well, let's say you just find a loudspeaker collecting dust in a closet somewhere. No markings on it, no model number. You have no idea what this thing is. You can't look up what its spec sheet says. And you just kind of want to get a sense of, well, how directional is this going to be? Well, you can just look at how big it is, and you'd get a sense real quick of what it could do. For example, that frequency, this loudspeaker up there, how big do you think that low frequency driver is? What do you suppose the diameter of that is?
6-inch, 8-inch.
6 to 8 inches, probably. Okay. Well, what frequency has a wavelength of 6 to 8 inches?
200-ish, 200-250.
Keep going, keep going.
0.5 equals 1,000.
So
500 hertz.
keep going. Guys, we did. How do you find out a wavelength?
1,000 divided by the wavelength.
1,000 divided by the frequency will get you the wavelength.
Yes.
To get to, if you know the wavelength and you want a frequency, you do the same thing. 1,000 divided by the wavelength. So if I'm saying the wavelength
2,000.
of 6 inches
2K.
be 2,000 hertz, right? 6 inches is half a foot. 1,000 divided by 0.5, 2,000. Okay, 2,000 hertz. We did this, right? We did this a couple weeks ago. So just without knowing anything about this loudspeaker, I would say it is not physically possible for that loudspeaker to control any frequency lower than 2 kilohertz. Anything below 2 kilohertz will be omnidirectional out of that loudspeaker, regardless of what's going on inside of it with the crossover and all that sort of stuff, because its physical size dictates that. So 2 kilohertz, anything below 2 kilohertz will automatically have to be omnidirectional for this. Okay, and I just know that. I don't have to look that up. I can tell it from its physical size. This one over here, it's a little bit bigger. So, it could potentially be directional for some lower frequencies lower than 2 kilohertz. Okay, we'd have to measure it and find out for sure. By the way, this is assuming the loudspeaker is not in a box. Right? This is open baffle. Okay? If you put it in a box, this is what happens. Okay? So same single driver, you just put it inside of a box, like any of these, and it starts looking a little bit different. It still gets narrower as the wavelength gets smaller, but it doesn't do that same lobing effect because the box helps with that wraparound, that destructive interaction that's wrapping around. Okay, but it's still, you can see it still gets narrower, but it evens out this thing that happens at the high frequency, so it's not beaming anywhere near as tightly as it used to before we put it in the box. So this is why boxes and horns and things are useful. Yes, they make it louder, but they also reduce, they're able to make it louder while reducing all of that sort of beamy, ripply stuff, okay, that can get in our way. So knowing this now, you might start to understand why we put more than one driver in a loudspeaker. Okay, most people sort of assume that, well, we put multiple drivers in a loudspeaker because not one driver can't produce all the frequencies. But that's not true. Think about that for more than about 30 seconds. Have you ever, in your life, listened to a single loudspeaker driver and heard all the frequencies? Kai's got something on his desk right now that does that. These little purple earbuds. There is one driver inside of that. You stick it in your ear, you hear all the frequencies, don't you?
But that's just because you don't need to control where they're going because it's so small.
Exactly.
All the sound drops away.
You don't need to control where it goes. The one driver can produce all the frequencies equally. It's doing it. You stick it in your ear, you hear all the frequencies equally. The difference is it can't control the dispersion of them equally. Okay? It can reproduce it equally. But in this case, you're taking that on-axis point and you're pointing it right at your eardrum. So you don't actually care what happens at other angles, right? Because all you're listening to is the 0 degree point. So that's why we have more than one driver. It's not because the drivers can't produce the frequencies. They just can't control the dispersion of them equally. Okay? So if we want to have a loudspeaker, so let's just say that this is the ideal dispersion that we want. We want the loudspeaker to do that across the entire frequency spectrum. Yes?
Well, yeah, but they're also like with lower frequencies, you can't produce those with small things because the diaphragm physically can't move enough to like.
Sure it can. You can hear 100 hertz coming out of that.
Yeah, I know, but I can't hear 32 hertz coming out of
Sure
that.
you can.
It's just really, really, really quiet.
Well, really, really quiet if you go off axis of it. Right? And yeah, I mean, there's a certain amount of excursion that it's got to do to, you know, to go that low, but it can do it.
Okay, but that's why all the headphones you look at always say 20 to 20K.
Yeah. Because they're like, yeah, it can do it.
Doesn't mean
It won't do it well.
Yeah.
Right. Well, it's just it's not that it won't do it well. It's just that you run into some sort of like physical limitations of like how far it can go, but it can do it. That little driver, remember, to make 32 hertz, it just has to move like this 32 times a second, back and forth 32 times every second. Well, it's doing it 1,000 times every second at 1 kilohertz. If it can do that, it can move 32 times a second. There's nothing that says it can't do that. But it's not about the loudspeaker. It's about your ears. Because remember what we learned last week? Our ears are less sensitive to low frequencies. So that little bud is reproducing 32 hertz, the same loudness as it's producing 1 kilohertz, but your ability to hear that is different.
Because you normally feel those low frequencies and you can't feel it.
No, because your hearing is not sensitive to the low frequencies. Remember the curve, the Fletcher-Munchausen curves? So, you know, you have to produce significantly more energy at low frequencies than you do at high frequencies in order for it to sound the same level to your ears. So this is a limitation of your hearing. We do not hear flat frequency response. We hear very unflat frequency response. So it's not the loudspeaker, it's you. The loudspeaker can produce all the frequencies. You can't hear them the same way, okay? So you need, if you want to hear 32 hertz louder, you need to get a loudspeaker that can move more air and get a higher amplitude so that you can hear it more, all right? So it's a misnomer to say that, you know, the little earbud just isn't big enough to produce 32 hertz. It is big enough to produce 32 hertz. You just can't hear it because of your, you know, the weaknesses of your hearing system. If you didn't have such crappy ears, right? If we hadn't evolved to have such crappy ears that aren't sensitive to 32 hertz, then we hear just fine out of those buds, right? So the real reason that we do multiple drivers is because of this. So if we want our loudspeaker to disperse the sound for all the frequencies in this way, then we would just say, okay, well, this is when the diameter of the loudspeaker is 2 times the wavelength. So if I want to control 2 kilohertz in that way, how big of a driver would I need? It would be a driver that is twice as big as 2 kilohertz.
So like double the size of that one.
Yeah. It'd be 1 foot, right? Because if the wavelength of 2 kilohertz is half a foot, then I would need a loudspeaker that is 1 foot big, 1 foot in diameter, to do 2 kilohertz. Great, 2 kilohertz solved. Okay, what about 4 kilohertz? So what's the wavelength of 4 kilohertz? 3 inches. So I would need a 6-inch driver to produce 2 kilohertz. Great, all right. So I'm going to get a 1 foot driver for 2 kilohertz and a 6-inch driver for 4 kilohertz. What about 1 kilohertz? I want to get 1 kilohertz to disperse that same way. I would need a 2 foot driver now, right? So on and so forth. So you could make, without any horns or anything, you could make a cabinet that dispersed all the frequencies at the same angles, and you would hit the 6 dB down point at the same exact time, as long as you could have enough drivers in there to be always twice as big as the wavelength of those frequencies. It'd be a lot of drivers, and then you'd have to sort of deal with the interactions and the overlap and the crossovers between them, but there's some loudspeakers in our shop that do this. Like we've got those big LA325s. How many drivers are in those?
5, I think.
Yeah. Now, in that case, they're trying to create a loudspeaker that sprays sound everywhere. Okay, they're not trying to control it. They're trying purposely to not control it. And so they are purposely picking loudspeakers that are smaller than the wavelengths of the sound that they're producing, so that they'll go everywhere. Same thing with these ones. They're doing that same thing. So these are called near-field loudspeakers. You're never ideally going to be listening to these more than a couple of feet away from them, right? Because they're studio. And so you don't want them to be very tightly controlled, because if you're only 2 feet away from them, you could move 6 inches in one direction and be really far off axis of it when you're that close. So they want these to spray everywhere. So they're going to put, what they're going to put out of this low driver is going to be frequencies that are larger than this, right? So this driver, if this is 6 inches, they're going to put frequencies 1K and below through this one, and then 1K and above through this little dinky tiny one, because this one's what, 1 inch? So that would be like 10 kilohertz or so. So between 1 kilohertz and 10 kilohertz, this little teeny one will also be more or less omnidirectional. So I'd be willing to bet that the crossover frequency for this thing is 1 kilohertz. That's where they decide where the frequencies go. Everything 1K and below goes through the big one. 1K and above goes through the little one. So that way the loudspeaker will be omnidirectional. Okay? All right, we're done. So what we're going to do on Monday is I'm going to show you how you can use this information to actually plot the dispersion of the sound on a CAD drawing of a theater. So you can pick a loudspeaker, plop it in there, and say, okay, where's the sound going to go, and how loud will it be at all the seats? Okay? That's it.